Welcome everyone for the post-tea session. So we have 5 talks here, and the first talk is by Professor Amitabh Virmani from CMI, Chennai. So Amitabh, over to you.
Okay, thanks. Can you hear me?
Yes, yes.
Okay. Yeah, I did not know whether I am muted or not. Okay, so yeah, let me start by thanking the organizers for putting together this conference and inviting me to speak. I will be talking about black hole hair removal for n equal to 4 CHL models. I will explain the phrase CHL models as I go along. Okay, so this is based on this paper that we put out last year and some work in progress. Okay, so here is the outline of my talk. I will give a broad introduction, motivation for our work, and a brief review of the papers our work is based on. Then I will present the supergravity analysis that we have done in order to construct these hairs. And these here we have constructed to resolve a puzzle for the CHL model. So I will give a statement about the puzzle of this hair removal puzzle for the CHL model, then the resolution that we have proposed. And then I will end with the summary and future directions. Okay, so let me start with the, so before I start, let me just make 2 comments. So this project grew out of Chennai Strings meeting in 2018. And this is based on a paper that we have done with biennial Chakrabarti. He was a postdoc at IMSC. Suresh Govindrajan and Yogesh Srivastava and CMI student 𝗦𝗵𝗶𝗶. Almost all the calculations were done by 𝗦𝗵𝗶𝗶. So she worked very hard in this project. And there is a concurrent paper by Aradhita and Justin David with the main result the same. Okay, so let's start. So black hole here, John Wheeler famously made the statement that black holes have no hair. And this statement has been made more precise over the years in what are called no hair theorems. So these theorems say that in the presence of no matter other than the Maxwell field, the black hole is completely described by mass, electric charge, and the spin. Even if you add matter, some version of these theorems continue to hold, provided the matter is not very exotic. If you add exotic matters, then of course the theorems change. In particular, for more complicated setups, such as setups involving Kaluza-Klein dimensions, form fields, all these things will feature in my talk. Black holes here are possible, and we would like to construct such here. So in our context, black hole here is defined as smooth, normalizable, bosonic or fermionic degree of freedom that lives entirely outside the horizon. Okay, so the phrase black hole here itself has several meanings in the literature. In our case, it is normalizable, goes to 0 at infinity. Is it smooth at the horizon, and also goes to 0 at the horizon. So it lives completely outside the horizon. There are many methods to construct black hole here. It's a big subject in general relativity. Okay, so why are we interested in black hole hairs? So our reason for being interested in black hole here is the relation between black hole here and the microscopic counting. So black hole entropy is in terms of black hole entropy in terms of microscopic degrees of freedom is insensitive to the nature of solution far away from the horizon. So if 2 black holes have identical near horizon geometries, they have the same degeneracy because they have the same near horizon geometry. And there is a apparent, at the same time, well-studied counterexample of this. This is BMPV black hole in flat space and BMPV black hole in top nut space. So there is a proposed resolution to this discrepancy in some sense, and the resolution goes under the name of hair removal. And this was proposed by these authors, Banerjee, Navamita Banerjee, Mandal and Sen, and Jatkar, Sen and Srivastava in 2009. So motivated by this, our work is hair removal for the CHL models. Okay, so I will not be able to go into the full details of our project. I mean, it has several elements, but I will give here a 2-line summary of what we have done. So in 2009 papers, these authors did not treat the rotation of the black hole in sufficient detail. In our paper, we have put in a lot of computational effort to fill in this gap, but this is not at all the topic that I will be discussing in this talk. And also, in these 2009 papers, the authors looked at the simplest model. We look for a wider class of n=4 models. And as you know, the generalization from K3 compactification to CHL models is sufficiently non-trivial. We will see that this hair removal story is non-trivial. Okay, so let me just say what are the models of interest. So we will be interested in models with n=4 supersymmetry. And these models provide a rich arena for such discussion. For a class of CHL models, black holes can be described in terms of 6-dimensional 2,0 supergravity coupled to n-t number of tensor multiplets. Okay, so what we will do is that we will start by looking at black holes and the hair to these black holes in these theories. Okay, this is what we will start with. Okay, and then the aim will be to construct a black hole here in this setup. Now, it turns out that discussing all possible here is hard, perhaps not even useful. Matching of the microscopic indices of 4D and 5D black hole may be possible with the knowledge of few here. And this is the attitude that we will take. What we will do is that for the 2 black holes, we will study only 3 types of hair. And we will see that once we take into account these here, we will be able to explain the difference between the 4D and 5D microscopic indices. Okay, so specifically the modes we will be looking at are the so-called 𝗰𝗵𝗶𝗿 modes, 𝗰𝗵𝗶𝗿 here. Then using the tensor multiplates, we will be constructing form field here. They all come from the tensor multiplate sector. And we will be looking at the fermionic here also. Okay, so this is the 1-slide summary of the work of 2009 papers of Sen et al. So on the left-hand side is BMPV black hole in flat space. On the right-hand side is the same black hole embedded in top-net space. So in top-net space, it admits here. And the aim of our project is to construct these hairs for these 4 general class of models. And once we construct these models, and then once we construct here for these models, we will see that the 5D partition function is same as the 4D partition function after removing the hair partition function. So 4D divided by the hair will give us the 5D partition function. Okay, so this is the picture to keep in mind. That we will be interested in constructing these wavy lines which account for the hair and which account for the difference between the 2. Okay, so with this brief introduction, motivation and review, now let me present the supergravity analysis that we have done to this end. So as I said, we will be interested, at least to begin with, we will be interested in 6-dimensional 2,0 supergravity coupled to n-t number of tensor multiplets. So this supergravity theory is sufficiently complicated. It has many fields. In the bosonic sector, it has metric, self-dual and anti-self-dual 2-form fields and lots of scalars. In the fermionic sector, it has gravitinos and lots of Majorana fermions. So both for the solutions and for the hair, what we will do is that we will only consider setups where scalars are set to constant values. Okay, and all the spin half fermions are set to 0. This is the setup in which we will be interested in constructing the hair. So this is sufficiently simple and manageable. And we will only be looking for solutions hair solutions which preserve 4 of the 16 supersymmetries, same supersymmetries as that of the black hole. Okay, so BMPV black hole. So as I said earlier, in our paper, a lot of effort has gone into rotating BMPV black hole. But in this talk, I cannot discuss those details. So I will focus on the non-rotating BMPV black hole. So 5-dimensional BMPV black hole lifted to 6 dimensions becomes a black string, and the string is in the x5 direction. There are four flat directions. So these 4 flat directions are DWI, DWI, and U and V are the null coordinates in this geometry, which capture the time and the black string direction x5. The 4-dimensional BMPV black hole is obtained by embedding the BMPV black hole in top-net space. And what that means is that we replace the 4-dimensional flat space metric with the top-net metric. Okay, so these are the standard coordinates for the top-net metric, where chi r is this function which goes as 1 over r, and there is a constant here which determines the size of the S1 at infinity. Okay, so this function psi that enters here is also 1 over r, but this r is the radial coordinate which is in the top-net geometry. Okay, this r is not the radial coordinate constructed out of these wi's. Okay, I mean, if you are familiar with the 5-dimensional black holes, you might say that it will be like 1 over r squared, the harmonic function. But here I'm using a slightly different radial coordinate, and this radial coordinate is related to this top-net r, and here it goes like 1 over r. Okay, so these 2 black holes have identical near horizon geometry. And what I will be doing is that I will be interested in constructing hair on these black holes. Okay, so what I will describe is the hair that we have constructed on these black holes. So the way I have organized this, I will first discuss the bosonic 5D hair, then fermionic 5D hair, bosonic 4D hair, fermionic 4D hair. So this is how these slides are organized. So let us start with the bosonic 5D hair. So bosonic 5D hair or hair candidates, they are constructed using the Garfinkel-Vachaspati transform. So Garfinkel-Vachaspati transform is a solution generating technique which maps a known solution to a new exact solution. And what this technique requires is a null hypersurface orthogonal killing vector. Okay, so satisfying all these 3 properties is not completely trivial. Few solutions satisfy all these properties, so that's why the Garfinkel-Vachaspati technique is not very widely applicable. But in our case, for the BMPV black hole in top-net as well as BMPV black hole in flat space, the technique is applicable. Both these black holes admit null hypersurface orthogonal killing vectors. Partial U is the vector that we will be using for this. So given that vector, we will do the transformation. The Garfinkel-Vachaspati transformation is new solution G prime is G plus T times Km Kn. Okay, where Km Km is this killing vector. K upper M is del by del U, and you just have to lower the indices. Okay, so where this T is the scalar field which satisfied box T equal to 0, and it is compatible with the killing geometry. Okay, so this was my 1-slide summary of the bosonic 5D here. For the fermionic 5D here, we solved the fermionic sector equations of motion and obtained the deformation in the gravitino. And we will work, to begin with, we will work with the undeformed background. We will find the hair mode, and then we can go and check whether the deformed background also admits the same hair modes or not. Okay. So this is how we have organized our paper also. So first we find the fermionic hair mode for the undeformed background, and then we check whether that hair mode is also a valid hair mode with the GB deformation. So for the fermionic sector, gravitino with only V component is taken to be non-zero, and even the V component is taken to be independent of U, in spirit with the fact that it should be compatible with the killing symmetry. And we find a Hare mode in this psi alpha V. Okay, so now for the bosonic 4D, we again use the Garfinkel-Vachaspati method to find a class of Hare modes. But now, because we have the top-net space, new class of modes are possible, and these are coming from the tensor multiplet sector. And there are NT number of such modes that come. Specifically, the way it happens is that top-net space has a harmonics 2 form, harmonic self-dual 2 form omega Tn, and taking the wedge product of omega Tn with dV, we can construct a deformation which belongs to the tensor multiplet sector, and this gives rise to NT number of Hare. Okay, and in the same way we do the fermionic 4D. We find a solution that is independent of U for the V component, and we solve the same set of equation in the top-net background. It turns out that the top-net space does not have any effect on the fermionic deformation at all. Exactly the same equations, literally exactly the same equations go through, and we find the same Hare modes. Okay, so now all these modes that we have constructed, now we have to check whether they are valid Hare modes or not. And for this, we have to do 3 things. We have to check whether the modes are smooth or not, smooth near the horizon. And the way we will do this is that we introduce suitable coordinates which are smooth across the horizon and check whether the modes are smooth in those coordinates. The next thing we have to check is whether the modes preserve the right amount of supersymmetry or not. So in particular, no additional supersymmetry should be broken. And for this, we have to do the killing spinner analysis with the deformation added. And the next thing we should check is that the modes are only supported outside the horizon. This was our definition of the Hare. So all of these smooth deformations should vanish at the horizon. So once a mode satisfies all these 3 things, we will say that such a mode is a proper Hare mode. Okay, so when we do these calculations, we find that all the modes for the 5D black hole that we have constructed, they are supported outside the horizon, but the Garfinkel-Vachaspati modes, they are not smooth across the horizon, so they should not be counted as Hare. For the fermionic modes, we find there are 4 Hare modes. For the 4D black holes, we find there are 3 Garfinkel-Vachaspati modes, which should be counted as Hare. So that's why I have written them in green color, and they are parameterized by these functions GIV. And for the fermions, exactly the same analysis applied. There is no difference. So we again find the four modes. From the tensor multiplet sector, each tensor multiplet gives rise to 1 Hare mode. So we find NT number of Hare modes. Okay, so here is the summary. So we have done explicit construction of Hare modes for the 4D and 5D black holes. These are nonlinear solutions. I mean, all nonlinearities are taken into account. And this is the spectrum that we have found. So for the bosonic, we find that there are no Hare mode on the 5D black hole, but for the 4D, there are NT plus 3 number of Hare modes. And for the fermionic sector, both of them have the same number of Hare modes. Okay, so questions, comments on whatever I have said so far? Okay, so now let me state the Hare removal puzzle for the CHL model. So these Garfinkel-Vachaspati modes and so on, these things I have been working on for several years. And in 2018, at the Chennai Strings meetings, I was giving a talk on construction of some Hare modes for a different setup. And then Suresh commented that the Hare partition functions are closely related to the 𝗰𝗵𝗶cie partition function. Okay, and this is something I did not know at that time. And from there, this collaboration started, and we started exploring how these hair modes that we are talking about are related to the CHL models and the half BPS partition function. Okay, so it turns out that for the K3 compactification, the half BPS partition function, same as the hair partition function, is eta rho 1 over eta rho to the 24. And if we think in the in terms of these languages, this language, then this is essentially what Sen et al. Had done in 2009. They explained this eta rho to the 24 from a hair analysis. And the way this works is that for K3 compactification, there are 21 tensors. Tensor multiplets one gets in 6 dimensions. And if we go back and look at this NT plus 3, this is what give rise to the 24 extra bosonic modes, and this is what enters in this eta rho to the 24. So, so the extra bosonic hair modes is what explains the difference between 4D and 5D particle functions for the K3 compactification. Okay, for the CHL models, things are a little bit more subtle. So let me first say what these CHL models are. So the CHL stands for Chaudhary, Hockney, and Likin. These are some sort of orbifold models. The key feature of these models is that they have smaller number of vectors, say in 4D, or from the 6D point of view, they have smaller number of tensor multiplets, not 21, but smaller number of tensor multiplets. And then the K3 compactification. And these models are obtained by Zn orbifolds of certain Zn orbifolds of K3 times S1 times S1 tilde. The orbifold group acts as an X on the element of the cohomology of K3 on the self-dual and anti-self-dual harmonic forms, and it also involves a shift along the S1 direction. Okay, so now let us ask how many hair modes we are able to construct, and what is the expected hair partition function. So, well, natural place to start would be the 6D supergravity description, because this is the description in which we know how to construct the hair modes. So this is what we did. So we obtained the lower dimensional 6-dimensional supergravity description of these models. And then we just constructed the hair modes for the G invariant fields. So let's say for the Z4 CHL model, the number of tensor multiplets is 7. So what we have is NT plus 3, that is 10 extra bosonic hair modes. But how do we obtain the hair partition function, which is the half BPS partition function, this slightly complicated object? You see, it has a lot of feature, and there is no obvious relation to the number of G invariant hair modes that we are able to construct. Okay, so the resolution. So the resolution of this puzzle lies in thinking about the hair modes in 10 dimensions. So let us schematically denote Y to be the K3 directions and X to be the remaining 6 dimensions which we have used so far. Then in 10D, the Riemann-Riemann form fields schematically decompose as C4 is like C2 wedge omega. Okay, where omega are the self-dual and anti-self-dual harmonic forms on K3, and C2 are the fields. I mean, if you restrict yourself to G invariant modes, then C2 are the tensor multiplets that you will see in 6 dimensions. So on the elements of the K3 cohomology on the harmonic and on the self-dual and anti-self-dual harmonic forms, the orbifold group will act. So let's consider the Z2 CHL model, and let's try to understand this for the Z2 case, that is the simplest. So in this case, the orbifold group of order 2 will act on these quantities. So the way it will act is that there will be 8 anti-self-dual harmonic form omega gamma that will have eigenvalues -1 under the Z2 action. So out of these 19 anti-self-dual form, 8 will have -1 eigenvalues and 11 will have +1 eigenvalues. So this is for the C4, but then there is a similar story for the 2-form B field and all of those things. Okay, so if one takes all of that into account, then one finds that there are 13 tensor multiplets for the Z2 model, and as a result, NT plus 3, so there are 16 extra bosonic modes from the G invariant sector. And now there are 8 self-dual harmonic forms which have eigenvalue -1. So there are 8 modes which 8 here modes which can be constructed with boundary conditions along the orbifolded S1, such that when you shift, that is the CHL action, under the CHL action, the C2 comes back to itself with a minus sign. Okay, so omega gamma has eigenvalue -1, and C2 under the CHL action also comes back to itself with a minus sign. Okay, so as a result, we have 16 bosonic Heer modes with periodic boundary condition and 8 bosonic Heer modes with antiperiodic boundary condition. And in correct quantization of charges, the periodic modes contribute even units of momentum along the S1, and the antiperiodic modes contribute odd units of momentum. So if we take this into account, can you hear me, Chandra?
Yes, briefly I could not hear. Now I can hear.
Oh yeah, actually the power just went. So okay, so so for the Z2 CHL model, the way this works is that so there are 16 periodic modes, so 16 even units of momentum modes. So Q, they contribute Q to the 2, Q to the 4, and so on. And then there are 8 antiperiodic modes, so they contribute odd units of momentum. And taking both of these Heer modes into account, we indeed get the half BPS partition function to be the Heer partition function. Okay, there are some more details, but the essential idea is as above. We indeed get the Heer partition function to be the half BPS partition function. Okay, so let me just end my talk with the Z4 CHL model example. So in this case, as I was saying earlier, there are 7 tensor multiplets. So there are 10 modes with no twist. And then one looks at this Chaudhary law paper and figure out how many 2 pi I over 4 twist modes and so on. So in this model, there are 4 modes with 2 pi I over 4 twist, 6 modes with 2 times 2 pi I over 4 twist, and 4 modes with 3 times 2 pi I over 4 twist. So when one takes all of this into account, this is how the counting goes. So for momentum modes, which are quantized in units of 4, we have 10 such modes, 10 such here. So we get for 4, 8, 12, and so on, we get 10. For 2 pi I over 4 twist, we get 4 modes. And for these twists, we get 6. And for the other ones, we get 4. So when one takes all this properly into account, we indeed get eta to the 4, eta 2 rho squared, eta 4 rho to the 4. I mean, you can see this like 1, 2, 3, 4, like these come with the power 4. And then some powers are left here, and those combine into this and this. Okay, so we indeed get the Heer partition function to be the half BPS partition function. And this is all I wanted to say. Let me just end with the summary and future direction. So for the CHL model, the puzzle of 4D versus 5D index mismatch is slightly more challenging due to the presence of twisted sectors. And in our project, we have identified Heer modes in the untwisted as well as twisted sector. We show that after removing the contributions of the Heer modes from the microscopic partition function, the 4D and 5D horizon partition functions agree. Although I did not discuss this in this talk, but special care is taken in our paper to present details on the smoothness analysis of hair modes for the rotating black hole. And this is really the main calculation that we have, a lot of calculations we have done in this regard in our paper, and thereby filling an essential gap in the literature. So this is work in progress. So now we are looking at two-state twining partition functions. So using the ideas which are central to the CHL model, one can define a richer class of partition functions. So these are called two-state twining partition functions. It was done by Ashok Sen and Suresh Govindarajan in 2010. The counting is known for these objects, and a similar hair removal calculation needs to be done for these cases. And we think that we have understood most of the story. We are coming together to write the paper. So this is work in progress with Abhishek Chaudhary from IIT Bhubaneswar, Sutapa, 𝗬𝗫𝗀𝗃𝗀, and Suresh. Okay, that's all. Thank you.
So thanks, Amitabh, for a very nice summary. Questions, please?
Yeah, I had a question, if I can.
Yes, please.
So Amitabh, just is very nice work, looks like. Is there an analog in 3 dimensions, like with supersymmetric BTZ black holes or something?
The extremal BTZ black hole is supersymmetric.
I mean, only if you have a supersymmetric theory.
Yeah, in a supersymmetric theory, yeah. But whether this hair removal analysis can be done for such a setup, this I am not aware of.
I mean, it should be doable, right? It can't be harder than 4D and 5D.
Yeah, no, I mean.
Or is it trivial? I mean, the only possibility is that there is no hair for some reason.
No, I mean, there might be hair, but what will you compare? I mean, so here the puzzle was that for the biennial black hole in flat space and biennial black hole in top-net space, the indices were different.
Okay.
Yeah, so in that case, I don't know what would be the corresponding statement.
So you have to find the microscopic. So what is known about the microscopic index for the supersymmetric BTZ? Is it known beyond the leading term?
I would think so. Yeah.
Okay. Thanks.
Yeah.
So any other questions? Okay, so if not, let's thank Amitabh.
Okay, thanks.